In this video, we are going to look at two types of methods of integration. The first one being U-substitution, the second one, trig substitution. So let's quickly look at U-substitution. So we can look at this problem now. It's actually integral of x over x plus 1 all squared there. So, okay, when we are using U-substitution, if you have been watching my videos, you probably will have realized by now that U-substitution can be used differently. So you just have to find a way to be able to master it. And U-substitution is very useful in integration. So in this problem, we are going to use it like this. We will let U to be x plus 1. And now, when we solve for x there, we get that x is actually u minus 1. And then, when I differentiate this now here, I'll get that du over dx is actually going to be just 1. Then I can actually solve for du. If I take dx to the other side, just multiply by that 1, it's going to be du is equals to dx. So the reason why I did this, I want now everything to be in terms of u for me to be able to integrate. So where I see x, I will put u minus 1. But on the denominator, I don't have to replace x. I only have to replace the whole thing because I have x plus 1 as u. So it's going to be u squared. Now my dx is equal to du. So this now can be broken into two parts. We have it like that, minus 1 over u squared. Of course, we can multiply them like that to show that we are still integrating. Then this can be simplified further before we can integrate. 1 over u minus u to the power negative 2 du. Then this now is integratable. We can go and look at our formulas. 1 over u is actually going to be ln u, and then minus u to the power negative 2, it's just going to be plus 1 over u. Then we need to have plus c. Just note that in this one, we said that it's actually u to the power negative 1 plus 1 divided by negative 2 plus 1. And then it's going to be actually negative 1 over negative 1. So the sign will change. But at the end, we need to substitute back the x because we only use U-substitution to be able to help us to integrate, because we saw that when we tried to integrate it while it was still in the x form, it was a bit difficult to integrate. So now we need to replace u again. We said that u is x plus 1. It's x plus 1 plus u again is x plus 1 plus c will still stand there. So let's again look at how we can use U-substitution method again on a different problem. The technique, it's a little bit similar, but we will see that there will be a slight difference from the previous one. So if we're having integral of x plus 2 sine of x plus 4x minus 6 dx. So we can see that this is integratable even if we don't use U-substitution. So I will show that after I have solved it with U-substitution. So this time around, if I let my U to be what is inside the sign function there, it's going to be U x squared plus 4x minus 6. Then I can differentiate this to be equal to 2x plus 4. Of course, I should have dx here. And I can solve for dx. It's going to be du over 2x plus 4. Then I can continue to solve further. I will have du over, if I factor out 2, I'll have 2x plus 2 here. Then, in this case, you can see that I have let u to be equal to x squared plus 4x minus 6. But I didn't solve for x in this case like I did in this one here. Here it was very useful for us to do it like that. But now here, I'm not going to solve for x. I'm just going to substitute what I have here and see what is going to happen. Now we have I equals to integral this x plus 2. We leave it there. And then we said that now this we replace with u dx. We said that it's actually equal to du over 2 into x plus 2. So we can see that this now cancels out. So now our integral is actually in terms of u. So we can factor out 1 over 2 and write it like this, sine u du. And this now, it's actually integratable because we know that the integral of sine u is actually negative cos. So we'll have negative 1 over 2 cos u plus c. Then again, because we were having x variables from the beginning, we need to change back to our original variables. So we have 1 over 2 cos. We replace u now with x squared plus 4x minus 6 plus c is still there. So I think now this is good enough, but also you can do the same problem without having to go the long way of U-substitution if you know how to use this method properly. So we are having sine x squared plus 4x minus 6 dx. So, okay, here we know that integral of sine f of x dx is actually cos with a negative cos f of x plus c. This is very short, but we need to know how to use it properly. So I can see that, okay, I need to check that the f of x, I should get, if my f of x is this, when I differentiate this, I should get f prime here to be correct. So if I say my f of x is actually x squared plus 4x minus 6, when I differentiate this, it's going to be f prime equals to 2x plus 4. So I can see that it's actually not x plus 2, but I can factor out 2 here. Then I will have x plus 2 if I factor it out like that. So, meaning that for me to get there, it means that I must multiply by 2, right? So okay, if I have I can make this one here to be the correct derivative of f of x by multiplying it by 2. So when I multiply by 2, I'll get 2x. If I multiply x by 2, I'll get 2x. If I multiply 2 by 2, I'll get 4 sine x squared plus 4x minus 6 now dx. So because I have multiplied it by 2, I have to divide here by 1 over 2. And then from here, I can integrate now using this formula because it matches correctly. So I will have 1 over 2 that is outside. Then change this to be cos of x squared plus 4x minus 6 plus c. So this is very short if you know how to use it. Here it seemed as if maybe it was a bit long because I was explaining how it works. So actually from here you could have just say I is equals to 1 over 2. Then you change that to be 2x plus 4 like that, like this. Then 4x minus 6 dx. Then you write your answer here to be negative. But this is if you know how it works. So now we have actually looked at the main purpose is actually we wanted to look at U-substitution, and the scope was that we also need to look at trigonometric substitution. So let's look at trigonometric substitution on the following page here. So it's trig substitution. So trig, it's actually trigonometry. So we know that we have those inverse formulas, which are maybe if we look at this one here, 1 then dx is equal to x sine x plus c. So when we are dealing with trig substitution, it is mostly used to prove these formulas. So there is a way to prove that actually this actually equals to x sine x plus c. So here, if they say prove that this is equal to this, it's very easier now because you can see this is x sine. So if the question says prove, you'll just say x is equal to sine y. So, but some people, they can use theta. So let's use y because mostly in mathematics, when as beginners, we are used to x and y. So we can see that the x is equal to sine y. Then if I want to make y the subject of the formula, it's going to be inverse sine x. Then, okay, if I want to differentiate this now here, it's going to be, when I differentiate sign, it's different from when I'm integrating. Now I'm differentiating sign. It's not going to be a negative. It's going to be cos y dy. And you have to know that dy there, it comes out like this. It's actually dx over dy. So when you take it, when you multiply throughout by dy, it's actually going to come here as dy. So now we can replace everything to be in terms of y. So we said that 1 over the square root of 1. X, we said that is actually sine y. So it's going to be sine y square. And then we said that dx is cos y dy. Then when we continue here, we can have this here to be cos y dy. And then this, we just rewriting it. It's going to be sine square y. So, okay, let's continue. We know the identity sine square. Let me just, this is sine square theta plus cos square theta is equal to 1. Then cos square theta, it's actually going to be 1 sine square theta. Then even, let's say we're having cos square y, it's going to be 1 minus sine square y. So even here we can replace that by cos square y. So we will have now cos y dy over the square root of cos square y. Then we can see that the square root of cos square y will just give us cos. So this can cancel out with the cos on the numerator. Then when we continue there, we will have now only dy. And then dy is going to be equal to, when we integrate dy, we just get y plus c. And then we have said that y is equal to arc sine x. So now we have proved that. So let's look at another formula that we can prove. So actually now we are not proving. So the question says find I is equal to dx x square minus x. So actually, when it's like this, you already know that this is actually equal to, if you go and check, you have to, the guide is that you must look at your formula data sheet, your formula sheet there. This is equal to this when you look at that. So you have to look at the formula that has a square minus x square. Some will actually, the formula sheet, in the formula sheet, it can be written like this: a square minus f of x square is equal to arc sine f of x over a plus c. So it looks like, so we know that now already we are dealing with a sine. So the best thing that we do to solve that, to prove that is equal to this, we will let now x is not just going to be sine y, but because we have this constant here, a, we'll say a sine y. Then when we solve for y, it will become, so actually we can divide both sides by a, and then this side will have sine y. Then when we solve for y, we can see that now it's going to be arc sine x over a. Then again, we can see that from x is equals to a sine y, we can find dx over dy, dx over dy, which is going to be, a is a constant, so it's going to be, it's exactly the same as what we're doing previously, but then difference now is that our constant is a. So dx is actually going to be a cos y dy. Then we can go ahead and replace back. So now we'll have I is equal to, we replace dx there as a cos y dy. So a square is there, we leave it there, we only replace our x, which is going to be now our x is actually a sine y, the square is there. Then we can continue to solve. We'll have a cos y dy. If we factor out a, but let's start by having a square minus, if we square there, we'll have a square sine square y. Then we can continue to have a cos y dy. We can factor out a square now. A square is going to be 1 minus sine square y. So we can see that a square, the square root of a square is just going to be a. So it's going to cancel with that a. And then now this we have already seen that 1 minus sine square y is actually going to be cos square y. But because it's inside the square root, it will cancel with cos y there. Then we'll end up having just dy. Then when we integrate dy, we get y plus c. Then we can replace y with arc sine x over a plus c. So we can look at the last one quickly. Let's look at a different one. Let's not look at sine. Let's look at the one for tan. So when we look at this formula now here, the question says prove that this is equal to arc tan x plus c. So we need to prove. So the guide is we can check this. If it was not, the question was not given as a proof, maybe they say find the value of this, then you can look at the formula. You can see that the formula that matches this, it's actually this one, a square plus f of x square 1 over a arc tan f of x over a plus c. So, but you can see that now the constant is not, it's just 1. So perhaps it's just going to be just 1 plus f of x dx here, then just 1. So it's just going to be arc tan f of x plus c. So, okay. So how do we prove that? What we need to do is that we can let x to be tan y, like we did previously. The pattern is still the same. we solve for y, it's actually going to be arc tan x. Then we differentiate here. We know that when we differentiate tan, it's going to be sec square y. Then we'll have dy there because it's dx over dy. Then we take dy to the right hand side. It results into that. Then now from our original problem, we replace dx with sec square y dy over 1 plus, so our x is tan, so it's going to be tan y square. Then we'll have sec square y dy over 1. So this is actually going to be tan square y. 1 plus tan square y is sec square y. This is a trigonometric identity. So we can see this cancels out now. So we are left with dy at the end. When we integrate dy, we get y plus c. So we have said that y is arc tan x. So c is there. So that's it for today. We will end here. On the next video, we will look at a method known as T formula. So thank you for watching. Please like the video and comment so that I can know where to improve. And please do like this video and subscribe. Thank you until we meet again.